meet you at this conference, fourth International Conference on Material Science and Engineering. This is my contribution regarding the mechanism of adhesion and strength in traditional ceramics. I am Dr. Roberto Alejandro Rojas Holden from Engineering Faculty at Universidad Nacional de Asunción. Well, we did this with the purpose of having a physical mechanism of clay adherence to sand during the process of kneading, drying and firing in manufacturing ceramics in order to lead to extend our previous contribution to a theory that explains the interaction of both phases and how they work to achieve mechanical properties and lead to absorption, important requirements for the quality of these traditional ceramic products. We find ceramics with material from Paraguay and Chaco and the eastern region in Paraguay. We have tested and do some samples at different temperatures at the oven, about to nearly 1,000 centigrades, each 100 grades centigrades. We use also SEM analysis to find that the theory is okay. Yes, we try to find that in this research. So we have that ceramics is normally generally crystalline and has been bonded ionically or covalently or have both types of bonds. Well, these bonds may be stable or not stable, some more stable than others. We see here the stable ones. That will be the ionic, maybe covalent, some of them, and some of them are not stable. So it depends on the sizes of the ionic particles. Yes. The third claim is not only a mineralogical connotation, but it's about its particle size. We are going to use also sand and silt to represent the sizes of the raw material for the ceramic. For example, kaolinite has a combination of micacea, chloritic, and illite, partially isomorphic substitutions and combination. Sometimes the silicon ion can be replaced by an aluminum ion, and the aluminum ion in the octahedral sheet by iron, magnesium, zinc, nickel, and other ions. The phenomenon of absorption and adsorption is a chemical interaction between the absorbent, in this case the clay, and the liquid or gas absorbed. Clay can absorb more than 100% water of the weight. Kaolin comes from a kaolin clay, granite, or dense sandstone, which is necessary to process to enrich in minerals of the kaolin group. Methodology. Some were obtained from deposits used by ceramic industry from the Chaco and from Tobatí in Paraguay. And we did samples from 500 centigrades, every 100 centigrades up to 1,000 grades centigrades. We also use some microscopic analysis and some SEM analysis to the samples. Here we are preparing the samples, yes, of one of the, we did 3 of these materials. This was from the Chaco mud, and the other from Tobatí mud, and the third one was a mixture of 3 different raw materials. One the mud, one named Jobaré in English, and in Guarani language, and other is the, how you say, the one that gives color to the ceramic. Here are the tests of Poyocos, and the theory was this one before. This was the mechanism of adhesion known before this research. Here we have the Chaco mud. Well, one of the bricks were made of this. The other was M3, mud, Tobati mud. And the other, the fifth one, was a mixture of 3, 2, and 4 in this order. 90% mud, 5% kaolin, and 5% jovare. So we made by Boyocos, classify the soils, yes. Loamy clay silt has more silt than clay and sand. Silty clay has more clay and much sand also. And then sand silty clay, and sand silty clay from the Tobati. So we made the mix here is M5, sample 5. This was the infrared spectrophotometry of mud Chaco, M1. This of M3. And here are the X-ray diffractometry results from M1, from the Chaco sample. It was a potassium, sodium, calcium, magnesium, aluminum, iron, silicon, oxide, hydroxide. And here is his formula. And the aluminum silicate hydroxide also. M4 also, we have this. And there was a mixture of the others. So we have the results of the chemical analysis from the sample, yes. From the Chaco, Benjamín Aceval was the CT, and Tobati. The three that were mixed to find M5, sample 5. When compacting, the grains of sand remain with a smaller particle inside, and part of this enter the solvent sand. Picking the sand externally reveals a good adherence due to the binding properties of clay and the mechanical strength of sands and the mingling power of silt that also surrounds it externally. This phenomenon was observed during the production of mass kneading, and with the water added and its difficulty to go through sieve with 2.4 millimeters opening, different to when it passed through number 40 sieve observed before doing the sample tests. These were what was seen about 400, 500 degrees, 600 degrees, 80, 50, 100 degrees, and 1,000 degrees. And we're going to show these smaller parts are clay, these a little bit bigger are silt, and the sand borders are around here. This was a metallographic microscope we used to see this. This is a sample of Tobati M3, then M5 with a mixture of the three components of Tobati, raw materials. So we see here the compacted clay, these small particles, yes, all around here. We also see the silt, a little bigger, and the sand borders, yes. Well, and then we use a thumb where there is interaction between the other materials, yes, clay, silt, and sand in the borders. So we can see during densification and during sintering, during the sintering, the smaller sizes of the pores are reduced. And these are the bricks we made. We put that oven at different temperatures, and then we do the tests of these bending and compression tests. And we also did this for normal size bricks. Here bending, and here compression tests. These are the results of the reduced scale bricks from Chaco. And also here we see the density growing up. This is about the compression strength is here. Normally it goes out, this one. The density is here, blue one. The bending moment are these. So we have an absorption about here, up here to 850, more absorption. But the bricks are made about Chaco mud here, 750 or 1800 degrees, so centigrades. So here we have the compression, a good compression. So they about more than 6 megapascals, and these are used to produce the bricks. Also from mud from Tobati, we have here the compression. It goes up about 1000 centigrades, but you have at 700, you have a good strength also, but the strength goes better at 1000 grades. This was noticed here in M5 from the same Tobati. We have a good strength here at 700, so they use 700 to produce this mix of M3 Tobati sample, M4 and M2 from Tobati, and this is they use this value for strength. We have also absorption there, and we have also the other properties. Bending is the violet line, and the unitary mass is a green line, and the density is the blue one at the bottom. So we can see the compression load about real bricks, real scale bricks, and we see here the M1 sample, the M5 sample in red, and the reference, which is a brick produced at the Chaco City. Here we have the load bending and the deflection of sample of bricks. This is M1 from Chaco. This is M5 from Tobati, and this is a reference brick we use. Also, we more than taking the bending strengths and the shear strengths, we obtain the elasticity Young modulus, the rigidity modulus, and the coefficient of Poisson ratio, and the strength compression. This is in kilogram per square centimeter. So this is 11 megapascal, 7.8 megapascal and 9.8 megapascal. So with this, we compare the strengths of the bricks, and they give us enough strength for use the construction Asunción. This is A category according to Paraguayan standard. This is category B according to Paraguay standards, and this category A through for Paraguayan standard. This is the reference one. This is from the Chaco, and this is from Tobati. These are the bricks finally produced by them, by this, and we did it also in small samples. So here we have the small pieces of clay getting inside and pickering the sand and also the silt. They are inside and outside and uniting the sizes also, all the sizes. Well, here we have a kaolinite and an illite. Illite is from the Chaco and kaolinite is from Tobati. There is a small difference here that depends on the aluminum hydroxide that is also unite these particles here at the illite. The densification we see in these materials, that is more when we have more centigrades. Here, the densification is even greater. We have also take some SEM microscopy, and we use to put in little points the clay. This is the silt, and these are the sand borders. The sand borders are these. We have here the sand borders. So with this, we show that our theory of how here is the results of the samples by DRX by the Tulsa University at Oklahoma, the team of Dr. Hari Kumar. We see sample 28 and the phase quartz, hematite, illite, microcline, and hematite. This was seen on the sample. And the quartz here is the size in Armstrong. The hematite also his size in Armstrong. Microcline, illite, and hematite. And the percentage in weight, quartz 95%, hematite 3.5%. We have a conclusion. We can say that in a first stage of humidification and kneading, the sand received a contribution in its interiors and inlays in its exteriors of clays and silts. When compacted, this mix more intimately forming fundamental grains. During cooking, these grains grow due to thermodynamic expansions of the fundamental grains occur that join with their similar, reducing or practically eliminating voids and forming larger microscopic and nanoscopic grains. So we have here a combination of little clays inside and also outside, the same as silt that came inside the grains of sand, and also mixed with in the borders, on the sand borders, with the clay and the silt. They make a little strength with the change of temperature, yes, and in the mingling, in the kneading, they puncture the sand. Some of them stack in, other outside, uniting the pieces or the sizes to form the clay. So we like to know this. The morphology of the grains and particles at the nanomeric scale gives us an important clue of what happens when the water mixes with the raw materials and in the sintering process. If we could add particles, additive, or similar sizes or not, we could have composite ceramic materials not yet developed. The water acts as a glue in the kneading, and the fact of increased volume of sand grains with a little humidity, and that clay particles swim on that water are the first important part of the ceramic process. We have some evidence on doing ceramic at laboratory, controlling water percentage of the weight of raw materials, but we are on the way to describe the welding mechanism that gives durability and strength during sintering process. Finally, many thanks to you. In Guarani language, we say Awiyeterei. Thank you.